The term hypersonic traditionally refers to objects traveling at greater than 5 times the speed of sound. This velocity is an important area of study because of the chemical effects when traveling at these velocities, substantial heating, and unexpected pressure changes. These changes must be understood to create safe and effective vehicles. To understand the conditions in hypersonic airflow, engineers use two main approaches. Computational fluid dynamics is used to simulate air-vehicle interaction. However, it requires intense computing power. The other method is physical wind tunnel testing, where an increased cost comes with more results between design and condition changes. The first known aerodynamic testing devices were invented by Benjamin Robbins and Sir George Cayley, both men considered pioneers of aerodynamic study. These men made long arms attached to a rotating body to study the aerodynamics of different shapes. This paved the way for the Wright brothers to employ a similar method to find the optimal airfoil for their Wright Flyer. The first wind tunnel was created in 1871 by Frank Wenham. He observed that Newton's original aerodynamic theories underestimated the lift that could be generated by aerodynamic objects. This discovery encouraged many to contribute aerodynamic research with the use of the wind tunnel, including Osborne Reynolds, who deduced that scale models would create the same lift and drag as full-scale objects as long as the Reynolds number was kept constant between the two. The design of the wind tunnel varies depending on the speed of the air. This is because hypersonic air behaves like car traffic, while subsonic air behaves in the opposite way. To better visualize this, imagine if a highway shuts down to one lane. All the cars slow down, and once the lanes open back up, the cars travel much quicker. However, this changes as we design low-speed wind tunnels, as the section must converge to speed up the air. There are 4 main categories of wind tunnels: open section, closed section, blowdown, and single shot. An open section wind tunnel is one that takes air from the surrounding atmosphere and blows it out through the end of the wind tunnel. A closed section wind tunnel recirculates the air to be used again. While both are used in low-speed settings, closed-section wind tunnels offer better flow control. Blowdown tunnels use a pressure difference to drive the speed of the tunnel. With a high-pressure tank in the upstream and a low-pressure tank in the downstream, speeds of high subsonic to high supersonic can be achieved. Single-shot wind tunnels are driven by an extremely high-pressure canister separated by diaphragms that break at a certain pressure that are matched with specified Mach values.
To demonstrate our findings with real-world models, we constructed a scale open-section wind tunnel model out of common, everyday materials. The model features a fan, converging section, test section, and diverging section. The geometry of a wind tunnel is the key factor that makes it effective at producing high-speed airflow. The converging section changes the velocity of the air from low speed to high speed by changing the area of the throat. This process is reflected by the conservation of mass flow. To maintain a constant volume of air moving throughout the tunnel, the air must travel faster through the smaller areas and slower through the larger areas. We can take advantage of this property by placing our model within this region of increased airspeed. The equations that make our wind tunnel possible can be easily demonstrated by using your mouth and a piece of paper. Start by holding a piece of paper in front of you at an arm's length. With your mouth, make a big O shape. Now blow. Air should come out, but it won't be that fast. Now try it again, but slowly make a straw-size hole while blowing with the same force. As seen from the paper, the air jet will be more powerful. The apparatus shown was placed inside the wind tunnel to see how the air flows in the test section. The bottom strings are being blown toward the back wall, and the upper strings are being blown to the front wall. This means that there is a counterclockwise circulation in the direction of the flow. This is possibly due to instabilities in the airflow from the upstream. This can be fixed by adding a settling chamber or vanes to direct the air. In 1903, the Wright brothers were the first to achieve powered, sustained, and controlled flight. This airplane was constructed using different woods and fabrics. Aircraft at this time were based on unmanned gliders and mainly focused on generating enough lift to get off the ground. Later, the Junkers J-1 was made. Compared to other aircraft made of wood and fabric, the J-1 was completely made out of metal. This change completely revolutionized the aerospace industry. In 1935, German researchers discovered that sweeping a wing greatly increased the performance of the aircraft. Swept wings delay shock waves, lower drag, and add stability to the aircraft. The X-15 was a hypersonic research vehicle that flew from 1959 to 1968. Flying up to Mach 6.7, the geometry was crucial. The wedge-like fin increased the pivot control of the vehicle greater than it increased the drag. From blunt body theory, the aerodynamic heating on the vehicle's skin at hypersonic speeds can be reduced by rounding the nose of the aircraft. Our proposed change is for single-shot hypersonic wind tunnels. The diaphragms that separate the sections, when broken, release a high amount of energy that impact the walls of the tunnel. Adding replaceable plates to these areas allow for non-permanent deformation of the structure.